Hello everyone. Today I am talking about initial value problem and final value problem related to Laplace transformation. Then I will give the Laplace transformation of Bessel function and error function, and at last I will give you some examples related to the Laplace transformation. So far I have given you theorems related to the Laplace transformation, but in this lecture I will try to solve some questions. So let us start with the initial value theorem. Suppose that Laplace of ft and Laplace of f dash t exist. That means both ft and f dash t are piecewise continuous and both of them are of exponential order. And if Laplace of ft is equal to fs, then our limit t tends to 0, ft is equal to limit s tends to infinity s into Laplace ft. So this is known as initial value theorem because we are talking about limit t tends to 0. So proof. Please remember that the Laplace of ft and Laplace of f dash t exist. So we can use the formula for Laplace f dash t, which was your s Laplace ft minus f0. And now Laplace, you can expand this Laplace f dash t. So we will get 0 to infinity e to the power minus st f dash t dt. And in the right hand side we have s Laplace ft minus f0. So because we need the limits s tends to 0, so let us apply the limit s tends to infinity. So let us take the limit s tends to infinity. So we will get limit s tends to infinity 0 to infinity is equal to limit s tends to infinity s of Laplace ft. Now f0 is constant, so we can write it independent. Now here, as my f dash t is sectionally continuous and of exponential order, so we can take this limit as 0 to infinity limit s tends to infinity e to the power minus st f dash t dt equal to limit s tends to infinity s of Laplace ft. So now this e to the power minus infinity will be 0. So in the left hand side we have 0, and in the right hand side we can write it as and minus f0. Now this f0 can be written as limit t tends to 0 of ft. So on taking this term to the left hand side, we will have this result. So thus our limit t tends to 0 of ft is equal to limit s tends to infinity of s Laplace ft. So you can take this term in the left hand side, then we will get the result. Now we will talk about the final value theorem. For the final value theorem, let us assume Laplace of ft and Laplace of f dash t exist. And again, if the Laplace of ft equal to fs, then the limit t tends to infinity ft is equal to limit s tends to 0 of s Laplace ft. Proof is almost same. So let us start with the Laplace of f dash t, then we have this result. Now taking limit s tends to 0. Now let us take limit s tends to 0. Now if your s tends to 0, then we will have this limit s tends to 0, and here we will have limit s tends to 0 of s Laplace ft, then minus f0. So again this will be your limit s tends to 0 of e to the power minus st f dash t dt equal to limit s tends to 0 of s Laplace ft minus f0. So now this left hand side will not become 0 and we have integral 0 to infinity. Now this will be e to the power minus 0, that is 1, and this is equal to limit s tends to 0 s of Laplace ft minus f0. So from here we get, now try to integrate this term. Now the integration, here we have the derivative sign. Now after integration we will simply have ft and the limits are from 0 to infinity. Please remember that we are integrating with respect to t, and in the right hand side we have s Laplace ft minus f0. So in the left hand side we will have limit t tends to infinity f of t. For the lower limit we will have minus f0, limit s tends to 0 s of Laplace ft minus f0. Now this f0 will be cancelled in both sides. So we will have limit t tends to infinity ft equal to limit s tends to 0 of s Laplace ft. So this was your final value theorem. We call it final value theorem because we have taken limit at t tends to 0, that means at the upper limit. Now we have error function and then I will discuss the Laplace of error function. Let us define the error function. Definition: the error function of the variable t is equal to 2 upon root pi, then the limits from 0 to t, then e to the power minus some x square or u square du. So this is the error function of t. The definition of error function of t is equal to 2 upon root pi 0 to t e to the power minus u square du. So let us define error function of root t. I wish to find the Laplace of error function of root t. So I am defining this error function of square root t as this one. Now the Laplace of this error function of square root t is equal to 1 upon s square root of s plus 1. Square root of s plus 1. So this is the Laplace of error function of square root of t. So let us prove this result. So let us prove the Laplace of this error function. So before finding its Laplace, let us expand this e to the power minus x square. So error function of square root t is equal to 2 upon root pi 0 to root t, and you know that the formula for e to the power minus x is 1 minus x plus x square upon factorial 2 plus x power 4 1 minus x square upon factorial 2 plus 1 minus x plus x square upon factorial 2 minus x cube upon factorial 3 and so on. And the integration is with respect to u. So let us integrate this one with respect to u. The integration of 1 will be u. The integration of 1 will be u, and at the upper limit we will have root t, and for the lower limit this will be 0 because if we are going to put u equal to 0. Here the integration of u square will be u cube upon 3. So this will be your u cube upon 3, and then u cube means t to the power 3 by 2. Now at this point we will have 1 by the integration of u square will be this is your u power 4 because the e to the power minus x was 1 minus x plus x square upon factorial 2, then x cube means the power of u square, that means u6. Now the integration of u to the power 4 will be u to the power 5 upon 5. So the upper limit will be t to the power 5 by 2, and in the denominator we will have 5, and then 5 to the 10. So that is the integration of this one. Now let us find out the Laplace of this particular function. So the Laplace of error function of root t is equal to root 2.5. The Laplace of t power half, you know that we have the Laplace of t power n as gamma n plus half, gamma n plus 1 upon s power n plus 1. So the Laplace of t power half will be gamma half plus 1 divided by s power half plus 1. Then we will have 1 by 3 gamma 3 by 2 plus 1 upon s to power 3 by 2 plus 1. Then this will be 1 by 10 gamma 5 by 2 plus 1 divided by s to power 5 by 2 plus 1, and so on. You can write this formula for your convenience. Now you know that gamma 3 by 2 is equal to, this is your gamma 3 by 2 or gamma n plus 1. We know that gamma n plus 1 is n gamma n. So this will be your half, gamma half, and gamma half is root pi. And this is your s to power 3 by 2. So you can write it as s to power 3 by 2. Then at this place we will have 1 by 3, and this gamma n plus 1 will be n gamma n, that means gamma 3 by 2. Gamma 3 by 2 is half root pi, and here we will have s to power 5 by 2. And again here we will have 5 by 2, then 3 by 2, then half root pi divided by s to power 7 by 2, and so on. So let us take this term common. Now you can see that this 3 and 3 will be cancelled. Now this root pi and root pi will be cancelled. 2 and 2 cancelled. So we will simply have s to power 3 by 2. Now in the bracket, the first term will be 1. And for the second term, now this 2 is cancelled with this one. So we will simply have 1 by 2. This will be your 3 by 2. We have taken 3 by 2 common. So this will be your 3 by 2 plus 1. So you can see that this power will be your 3 by 2 plus 1, that means 5 by 2. And here we will have this 2 is cancelled with this 2. Now this will be your 5 to the 10, and then we will have 2 to 4 to the 8. So this will be your 3 upon 8, and s power 3 by 2 is already common, so this will be your s square. So this is your 1 minus half s plus 3 by 8, 1 by s square. Now we have a series of binomial. We know that the binomial expression of 1 plus x power n or minus n. If you expand this term with the help of binomial expansion, then this will be your 1 plus x power n, and that is equal to 1 plus nx plus n into n minus 1 upon factorial to the square of 1 by s. So you will find that the expansion of this one will be this particular region. So this is equal to 1 upon s power 3 by 2 s plus 1 upon s or minus half, and it is further equal to 1 upon s power 3 by 2 s upon root s plus 1, and so this is equal to s to power 3 by 2 minus 1. This will be your s to power 3 by 2 minus 1 square root of s plus 1. So this is your equal to 1 upon s into s plus 1. So I think there is some mistake, because we are getting square root of s. Oh sorry, we can see that this is your square root of s. So this is your half, 3 by 2 minus half, you can see that it is 2 by 2, and this will be your s. So this is your s square root of s plus 1. So that is the Laplace of error function. So this is your s plus 1. So now we will discuss about the Laplace of Bessel function. and in particular the Laplace of Bessel function of zeroth order. So let us define the Bessel function of zeroth order. You know that the Bessel function of zeroth order is 1 minus t square upon 2 square plus t power 4 upon 2 square into 4 square. This is the definition of the Bessel function, and you can find out it with the help of the general Bessel function of nth order, which is your j n x equal to summation r equal to 0 to infinity minus 1 power r1 factorial r into gamma n plus into x power 2 power n plus 2r. With the help of that result, we can find out this j0t. So let us evaluate the Laplace of this j0t. So the Laplace of this Bessel function of zeroth order is equal to 1 upon under root s square plus 1. We are finding this because we will need it later on to solve the ordinary differential equation. At that place we will need the inverse Laplace of 1 upon under root s square plus 1. So we are finding its inverse here, its Laplace here. So proof. So the Laplace of j0t will be the Laplace of 1 minus 1 upon 4, the Laplace of t square plus this will be your 4, 16, 4 job 64, then the Laplace of t power 4 and so on. We know that the Laplace of 1 is 1 by s, and the Laplace of t square is equal to, you know that the Laplace of t power n equal to factorial n upon s power n plus 1. So this is your factorial 2, that means 2 upon power 3. Then at this point we will have factorial 4 divided by s power 4 plus 1, that means 5. So if we take common 1 by s, then in the bracket we will have 1 by 2 s square, and at this place this is your factorial 4. Factorial 4 means 4 into 3 into 2 into 1, that means 24. So 24 by divided by 64. So this will be your 8 3 are 24 and divided by 8 and 1 upon s power 4. So again, proceeding in a similar way as we have done in the previous example, this will be your Laplace, this will be your the formula of 1 plus 1 upon s square minus power half because of the binomial expansion. So this is equal to s square plus 1 upon s square or minus half, and that will be your s upon under root s square plus 1, and so this is your 1 upon s square plus 1. Therefore the Laplace of j0t is equal to 1 upon under root s square plus 1. Now with the help of scalar property, with the help of change of scale, let us find out the Laplace of j0at. We know that the Laplace of f of at, I have already given this formula in my first lecture. This was your 1 by a f of s by a. So the Laplace of j0at will be 1 by a, and if this is your fs, then this will be your, the Laplace of f80 will be your 1 by a into the Laplace of ft, and s will be replaced by s by a. So here the Laplace of j0t is this one, so our s will be replaced by s upon a. So this is equal to 1 upon s square plus a square, 1 upon square root of s square plus a square. The Laplace of j0at is equal to 1 by a f s upon a, that means your s will be replaced by s upon a. So this is your answer. So that is all about the various definitions related to the Laplace transformation. Now I will try to solve the questions related to all these formulae. So let us start with the very simple question. Just try to evaluate the Laplace of cos square root t upon root t. Evaluate the Laplace of cos square root t upon root t. So for that I am expanding this cos theta with the help of binomial expansion, with the help of its formula. Then we will divide this cos theta by this root t, and then we will try to find out its Laplace transformation. So this cos root t is equal to, you know that the formula of cos x is 1 minus x square upon factorial 2 and so on. So this would be 1 minus x square upon factorial 2 plus x power 4, that means the square root 2 power 4, that will be your 2t square upon factorial 4 and so on. So let us divide this one by root t. So this will be your like this. So if we divide this by root t, then this will be your t to the power minus half. Then here we will have t power half divided by factorial 2, and then here we will have 2 t to the power 2 minus half. So 2 minus half, that means your t to the power 3 by 2, and then factorial 4, that means factorial 4 is 24, and so on. So just compute the Laplace of this particular term. So the Laplace of this series will be the Laplace of first term, that is Laplace of t to the power n, and that will be your gamma n plus 1 divided by s to the power n plus 1. Then in the next term we will have Laplace t to the power n as gamma n plus 1 upon s to the power n plus 1. Then in the next term we will have gamma 3 by 2 plus 1 divided by 24 into s to the power 3 by 2 plus 1 and so on. So this is your gamma half divided by the square root of s. So gamma half is root pi, so this is your root pi upon root s. Then in the next term this will be your gamma n plus 1 is n gamma n, so this will be your half root pi divided by s to the power 3 by 2. S to the power 3 by 2 can be written as s into square root of s. Then here we will have 3 by 2 into 1 by 2 into root pi, and here we will have s to the power 5 by 2. S to the power 5 by 2 can be written as square root of s into s square, like this, because this will be a 2 into power half, and that will be a power 3 by 2. So let us take this root pi upon s common. So in the bracket we will have 1 minus, now here we will have 1 by 4. So you can write it as 1 by 4s. So let us write it 1 by 4s. Now in the second term, here root pi upon root s is common. So we will have again 3 upon, here is the 24. So this will be your 3 divided by, well, if you divide 24 by 3, then this will be your 1 by 8. And you can also write it as 1 by factorial 2 into 4s square. So this is your 8, 3 8 is 24, 2 is 16, 2 is 32, and this 32 can be written as 16 2 is 32. So 1 by 4s whole square into factorial 2. Now here we can write it as 1 by factorial 1 into 1 by 4s. Why we have done all these things? Because we have the series of 1 minus x upon factorial 1 plus x square upon factorial 2, 1 minus x upon factorial 1 plus x square upon factorial 2 and so on. So this is the series of e to the power minus x. So our answer will be root pi upon root s into e to the power minus 1 by 4s. So this is your answer. Question: find Laplace t cos cube t. So we have a formula of Laplace t into ft. Now using that formula, let us find out Laplace t into ft. So you know that cos cube theta is equal to, just find out the formula of cos 4 theta. Cos 4 theta is equal to 4 cos cube theta minus cos 4 cos cube theta minus cos, this is your cos 3 theta equal to 4 cos cube theta minus 3 cos theta. So this is 3 cos t. So with the help of this formula, our cos cube t will be equal to cos 3t plus 3 cos t divided by 4. And now just find out the Laplace of cos cube t. The Laplace of cos cube t will be 1 by 4. The Laplace of cos 3t, the Laplace of cos 3t is s upon s square plus a square, that means s upon s square plus 9, plus the Laplace of cos t, and the Laplace of cos t is s upon s square plus 1. Therefore, the Laplace of t into cos cube t is equal to, so this is your fs. So if we write it as t into ft, where ft is equal to cos cube t, then you know that the formula of Laplace t ft equal to, we have already given the formula in the last lecture, that the Laplace of t ft equal to minus d by ds of Laplace ft. And here the Laplace of ft, that means the Laplace of cos cube t, the Laplace of ft means the Laplace of cos cube t is equal to this one. So this is equal to the derivative of this term, and that will be your minus 1 by 4 d by ds of s upon s square plus 9 plus 3s upon s square plus 1. So just try to differentiate this term and we will have the answer. So the differentiation of this term will be minus 1 by 4. The differentiation of you can use the formula of division rule. The differentiation of the numerator is 1, so multiplied by s square minus 9 minus s, then 2s upon s square plus 9 whole square. Then here we will have 3s s square plus 1 minus 2 s square divided by s square plus 1 whole square. So this is equal to minus 1 by 4. This is your s square minus 2s square. So you can write it as minus s square minus 9 divided by s square plus 9 whole square. And here you can write it as s square minus 1 divided by s square plus 1 whole square. Okay, then this will be equal to 1 by 4 s square minus 9 divided by s square plus 9 whole square. Then here we will have 3 s square minus 1 divided by s square plus 1 square. So this is your answer. So let us start with another question. The Laplace of, so this was your answer. Now let us start with another question, and which is your find the Laplace of t into e power minus t into sin t. Evaluate this. So if we take this one as ft, then this will be your Laplace of t ft. Now again, using the same formula of previous question, we will have minus d by ds of fs, where my fs is the Laplace of ft. And what is your ft? ft was e power minus t sin t. So this will be your Laplace of e power minus t sin t. So now I have already discussed about the first shifting formula. In the first shifting formula, we have given the Laplace, the formula for Laplace of e power at ft, which was your fs minus a, where fs was your Laplace of ft. In my previous lecture, I have given this formula. That means the Laplace of e power at ft was fs minus a. That means If we multiply ft by e to the power at, then our s will be replaced by s minus a. So here you can see that our fs is equal to the Laplace of sin t. In the Laplace of sin t, our s will be replaced by s minus 1, because here a is equal to minus 1. So your answer will be the Laplace of sin t, the Laplace of ft is equal to 1 upon s square plus 1. The Laplace of sin t is equal to 1 upon s square plus 1, but our s will be replaced by s minus a. Here we have a equal to minus 1. So here your s will be replaced by s plus 1. So this is the Laplace of e to the power minus t sin t. Laplace of e to the power at ft equal to fs minus a. That means in the Laplace of ft, that means in the Laplace of sin t, our s will be replaced by s minus a. In our case, a is minus 1, so our s will be replaced by s plus 1. So our Laplace t e to the power minus t sin t is equal to minus d by ds of fs. Fs means this term, s 1 upon s plus 1 whole square plus 1. So you can differentiate this one. Taking this term in the numerator, we will have power minus 1, and after differentiation, this power 1 minus 1 will come outside, and after differentiation of this term, we will have 2s plus 1 divided by its whole square. So s square plus 2s plus 1 means 2 whole square. So this will be the differentiation. So now let us start with the next question, and that is equal to question: find Laplace of 1 minus cos t upon t. So let us evaluate the Laplace of 1 minus cos t upon t. And you can write it as the Laplace of ft upon t, where my ft is 1 minus cos t. We know that the Laplace of ft upon t is equal to the integral s to infinity fs ds. We have this formula. So using this formula, now your fs will be the Laplace of ft. So your fs will be the Laplace of ft, that means the Laplace of 1, which is your 1 by s, and the Laplace of cos t, which is your s upon s square plus 1. So here we will have integral s to infinity 1 upon s minus s upon s square plus 1. So let us integrate this term. So now the integration of 1 by s will be log s. Now to integrate this term, let us assume s square plus 1 s t. So your 2s will be t, 2s ds will be dt. So s ds will be your dt by 2. So this will be your 1 by t. Now the integration of 1 by t will be log t, that means log s square plus 1, and the limits are from s to infinity. So we can also write it as log s plus, or you can write it as minus log. You can take this power, you can take this term in the power. So this will be your like this. So now log a minus log b will be your log a upon s square plus 1, and the limits from s to infinity. Okay. So if we try to evaluate the upper limit, then you can see that this is your log infinity divided by infinity, and that is your infinity, because log infinity upon infinity means you will have to take this s common. So taking this common, we will get s upon 1 plus 1 square, 1 plus 1 upon s square, then the limits from s to infinity. Now on taking s tends to infinity, we will have log 1 because this s will be cancelled. So now we have log 1 and log 1 is 0. So your upper limit is 0, and for the lower limit we will have to replace s by s. So there is no change. So we will have simply s upon under root s square plus 1, and you can also write it as log under root s square plus 1 upon s. So this is your answer.